All right. Okay, everyone. Hello. Welcome back to Fitted Technologies. Welcome to this video. So in this video today, we are going to simulate DCB test, double cantilever beam. Yeah, so it's basically a test to measure the interlaminar properties of composite materials. So it's a test method to measure the delamination resistance between composite plies. Okay. So in today's video, we're going to see four main concepts. First, how to model DCB, right? The second is that we're going to see how to model composite and isotropic material, how to assign material properties. And the third is how to use cohesive surface that is going to delaminate as we pull these two plies separately. And the last one is how to use MPC to model this loading block correctly. So let's get started. So so this is the idea, and this is the final results that we are going to find to simulate. Okay, it's nice. So let's now create a model. 3D deformable is standard 200, and then let's close this one first. The size, make sure it is 0,0, and this is 150,2, so it's in millimeters. Okay, and then click X and then click done. We will extrude in the Z direction around 20. That's the width of the specimen. Yeah, right. And then usually this will be tied with a block, aluminum block, and then we will pull the block, right? It's around 10 millimeters, and then there will be a pre-crack around 60. So in order to enable that, we need to provide surface. So we need to make partition, create partition here, hit datum plane, offset from principal plane. It's been a long time I didn't speak English, so my tongue is a bit stiff. Click here. So we're using here, okay. Offset from plane, okay. Enter value. We flip. So we're going to do it 2 times. The first one is 10 millimeter offset. This is for the loading block. Okay, let's check. Loading block DCB test, just to make sure that you understand what I'm saying. Yeah, so usually there's some kind of loading block like this, right? So you want to model that without physically modeling the block. Okay, and then let's make again plane to offset and their value. Click OK. Now this one 60. This one to provide pre-crack. Okay, so there's first here, there's second datum plane there, and then we are going to use these two datum planes to make partition. And click and hold, okay, and then there will be options like this, and then use datum plane. Select the first datum plane to cut, and then press the wheel of the mouse, press down, and then it means that you automatically click done, okay, without having to move your cursor here and manually click it. And then click again the cell to partition, press the wheel down, and then select the datum plane, press the wheel down, and then done. Right, so good. So now this is one plies or one side of the plies. It can be like 0,4 or maybe 0,8. Usually it's a 0, at least 0,04 symmetric or 0,8 symmetric. It depends. 0 means the orientation. If you don't understand what I'm saying, check my other videos about composite materials. So now let's copy this part because we need 2 of them, right? Copy, and let's call it part 2. Okay, so there are 2 parts. They're exactly the same. Now let's make the properties. So here the material is elasticity. We're going to use elastic anisotropic. So we're going to use engineering constant. Let's this is the property of glass fiber polypropylene. And put any values that is suitable for your materials. 4300, 0.34, 0.34, 0.4, 1700, 1700, and 1400. This is the matrix dominated shearing. That's why it has a lower modulus than the in plane shear. And then that's it. Yeah, we will not use the damage here because usually there is no damage in the ply, only in the interface. Then let's do it solid homogeneous, continue. Okay. And then let's define a section. Then click OK. And then choose. I supposed to click done. And then you click down. Or you can always press the wheel on your mouse down. Okay. And then click OK. Okay. Now it's good. Now what we need to do is to assign material properties. No, material orientation, I mean. So here, assign material orientations. Click here, click done. Use default method. So here, the if you just follow this, the first is the fiber directions. Click done, and then you go again for the second part. Okay. So when you use material orientations, for example, if you, in this case, the first directions is, how to say, is in the x directions. I don't know how to say it in English. Yeah, so how to say, let me remind. In Indonesian, we call it kebetulan. Uh, I forgot the English words for that. Uh, yeah, but imagine that if your fiber direction in the Z, and then you need to make some rotation uh, here when you assign this. Okay. For example, I will not do it, but let's check. I will not click OK, but let's imagine that your fiber direction in the Z, additional rotation direction. So you need to rotate in the 2 axis, right? And then maybe you need to use discrete, or not discrete, uh, Korean system. Yeah, 2, then the angle is 90. Yeah, so now the first direction is in the Z direction. That's how you set up arbitrary fiber directions. In this case, because the X is one direction, we don't need to do any rotation. And then assembly, click here. Let's make the 2 part, and because they are overlapping, they are in the same uh, location. Make sure you click auto offset so you can see that they are actually exist, both of them in the model. Click OK. You don't need, at the end we're going to assemble them correctly, but to make it easy, let's make some contact condition first. So let's go to the interaction. Let's go to the step first. Let's static general non-linear because they're going to be largely deformed. Okay, and then click here. Usually I'm using evenly spaced time intervals, so let's make 100. So we're going to have 100 frames. And then in terms of failure, I want to check, maybe, I'm not sure which one, for the cohesive one. So I will just use this 5 of them. Okay. And also energy for the history output, click here. Let's evenly spaced time interval 100, and then they will output all the energy. just in case you need it later. Okay. And as you've seen in my previous video, when you're modeling damage, you need to a little bit strengthen your solver by by modifying the solver criteria. Here we specify directly and change the default. For example, this is this some, I don't know, iteration maximum number that you allow. Usually it's 8 and 10, because sometimes it's difficult to converge, so you need to allow for more iteration. In this case, the IA is the cutback times how many times Abaqus should cut their time step to make it smaller. By default, if they cut 5 times and still not converge, they will show error message. Too many attempts has been made, or too many increments has been made, and error. And in this case, we allow for 20. So if they cut 5 times, it should be error. It's supposed to be error if we use the default. But in this case, it will try for the 6, 7 until 20 cutbacks. So it's more difficult to show error message. So Abaqus will try harder, harder, and harder to find the solutions. And let's go to interactions. We want to make a cohesive surface here. Here. So it's a surface to surface contact. So this is the master. So this is the loading block. This is the pre-crack. So there shouldn't be any cohesive surface there. Only here. Click and click done. And choose the slave type. Slave type is here. Also click done. And the contact interaction properties. Click here. And for cohesive surface, you need to use node to surface, I think, if I'm not sure. If you use a surface to surface, it will show error. And then click here to check the property, to input the properties. In original contact, usually you put tangential behavior and the normal behavior to prevent overlapping between models. But that's for general contact. Now we are not going to simulate the contact. We're going to tie them because we want to simulate the delamination. The tie will break once a certain stress level is reached in the delamination zone. So here we are going to give cohesive behavior. The stiffness, Abaqus know uh, to measure the correct stiffness, because this is zero thickness finite elements or zero thickness interface. So the value of the stiffness should be infinite or very large. So basically, it's not a material property, it's in zero interface. So usually people put number very big, like 10 to the power of 8 or power of 9. It's just like a numerical parameter to ensure the, how to say, the to ensure this sorry, to ensure the continuity of the displacement in the interface. Yeah, when you're using cohesive element, usually you need to put big value. Here Abaqus can't estimate their own value, so just like that. And then the damage, let's put 29 MPa. This is the typical value for epoxy actually. So imagine now the glass PP has been glued with epoxy, and there's a criterion. The easiest one is this one, maximum nominal stress. This is basically saying that if in the first direction the stress reaching a certain value, then the damage happened. The limitation of the maximum nominal stress criteria is that there is no interaction between stress in the first direction and the stress in the second directions. So it's not really good because there is no interaction. So what people use widely in the literature is to use quadratic fractions. So here, the stress in the second direction might affect the stress in the first directions. So damage can start earlier. Uh, Check my other video about cohesive elements. Okay, you might understand better than this one. And then specify damage evolution. I'm going to use energy, and I'm going to use 10. If you want to use a mixed mode, you can also use mixed mode like a BK, Benzegakenane. So in BK model, it's a mixed mode model. So each fracture mode has different fracture energy. So usually it's in mode 2, it's bigger than mode 1, right? So maybe you can use a 14, 14. But again, this is the DCB test, the one that we are going to simulate. So in the CB test, it's widely mode 1. So even if we change this 200, our simulation results later on will not be affected, because in fact, they are going to use this value only during the simulation, because this is dominantly mode 1. So let's put 20, but you don't care about this unless you want to simulate the real complex geometry where the delamination will occur under mixed mode. Yes, this will be affected. So how to get these parameters? Many people ask me. Check my other videos about these cohesive elements. The idea is that you need to do a DCB test for this double cantilever beam. This one you can use this, how to say, MMB, mixed mode bending test, or you can also use ENF and notch flexural test. ENF is the mode 2, pure mode 2. MMD is mixed mode. So this is uh, different types of testing to check the fracture energy for various damage mode. This is the viscosity. This is usually 10 to the minus 4 of the total period that you're simulating. Okay, and that's it. Click OK. Nice. And then click OK. Now they're already selected. Now let's go back to the assembly. Now let's assemble them. We're going to translate. Yeah, you click here, and then you click this guy, and then you click here. This point will move to this point. Yeah, and then check here and then click OK. Now it's good, right? Now let's go to the load. Yeah, so this is the last step, how to use MPC. But first, I will not going to use MPC. I will going to use the classical displacement-based boundary conditions. So basically, we are going to just pull this guy 100 millimeters above, okay? With the classical displacement. So here, I'm going to use displacement. This is placement. Click done. I will just fix this guy. And the guy here, I'm going to click here. And even if you want to enable this rotated in the Z direction, you can uncheck this guy. Let's uncheck this guy. Okay, the second one, uncheck. So let me explain to you what we are going to do actually is pretty simple. This is the DCB beam in the beginning. After the deformation, this guy will be like this, right? Yeah. So how to simulate this in the experiment? If you just pull that, like the one we just did, it will be like this. Let's change the color. It will be like this. So this part will be horizontal. Why? Because here, you give a constant displacement, for example, 100. And also here, 100. So all of them will move 100. So they remain horizontal even after you load. and it creates this kind of displacement, which is not like in the experiments. In the experiment, the blocks can rotate. So because usually there's a block here, right? And then there's a hole, and then there's a pin here that pulling up, and this block can rotate, so it will be curved nicely. So in order to achieve that, you need to use MPC, multi-point constraint. But here I will show you the effect of using MPC and not using MPC. First, let's not use MPC like this. Let's simulate. Let's go to mesh, and let's mesh. Let's go to the part one. This is straightforward global seed size. I'm using one. Okay. And then for the thickness direction, to make accurate simulations, you choose here and put by number. In order to simulate bending accurately, at least use 4. Here I'm using 5 to make it more accurate. And then click here. And then we're going to assign element type. We want to make sure that they are set up correctly. We're going to use second order accuracy, the hourglass control enhanced, so it's better under bending. And then click OK. Click done. And for the second part, the same thing. Here, global sheet part 1. Click OK. And then for the thickness, we're using 5. Okay, and click done. And then click here, yes, and assign element type. And then use enhance, second order accuracy, and click done. Click done. Okay, now let's save our job. Feed it 05. 05 means May. Okay, now they are safe. Now we can basically run the simulation without MPC. Okay, so this one is without MPC. I'm using 4 processor. Click here, job manager. Okay, and click submit. And it's gonna take some times. I'm going to pause the video, so the video will not be too long. Okay. Oh, here the power is not specified and small to 0. There is error. So as you see here, the power is not specified. Yeah, it's not really helpful. What power? But now I know it should be in this guy. Where is it? The interaction. This guy interaction properties. We in the damage we tell them that we use BK. So the BK specify power 1.2. So in BK power, it's a basically mixed mode evolution in the eliminations. So the value of the power is usually ranging between 1.1 to 1.5. In this case, I'm using 1.2. So you should get this value from fitting the experimental data based on MMB, mixed mode bending test. So, but for the typical value, just choose between 1.1 to 1.4 or 1.5. All right, all right. Now let's submit a job. Hopefully there's no error. Okay, it's running right now. It's gonna take some time. Let me pause it. Okay. It turns out I forget something, guys. Let's go back again in the interaction, not interaction, in the load. We didn't give any loading. In fact, we need to. Oh, this is the lower one. The upper one, in the y direction, we need to give 100 millimeter displacement, and then yeah, otherwise there will be no loading, right? Kill the job, and let's wait for it to stop, and let's check if it's already nice. Then let's submit again, and then let's pause the video again. Okay, it's still running, but I think we can already see the result, because in total we have 100 frame. Now it's already in 10 frames, so it's 10% dismiss, and click result already. And you can see here, it's very nice, right? It's deformed very nice. You click here like this. So as you see here, there is opening here, but the way the beam deflected was a bit strange. In the experiment, it should be like nicely curved like this, right? Straight like this, while this guy is now like this. Why? Because you give uniform displacement to this 10 millimeters beam area, right? So all of this beam here, they have the same displacement. In this case, it's still 10 because total is 100 millimeter displacement above. Now it's only 10%, so it means now they are deforming 10 from here. So this is what I mean. Yeah. So this is strange and this is wrong, right? You don't want to show this kind of simulation in your thesis or your tugas akhir or I mean undergraduate project or even your PhD dissertation. So how to fix that? Uh, we're going to use MPC to do it correctly without modeling the block directly. Okay, so that's the job running. We're going to compare later. So what you need to do, you need to go to the part. You need to make a reference point, tools, reference point, and then let's put the reference point here, or you can put any coordinate you want. But to make it easy, just click here. And for, oh, let's delete this. I'm not sure which one. For number one, okay, let's create reference point. I don't know which one should be below or up. Okay, not sure. Let's go to the assembly. Oh, we are wrong. Okay, okay, let's delete this reference point. Delete feature. Okay, done. Yes, done. And then tools, reference point, we need to choose this up. And for the second, we need to choose below. Click, we need to delete first here. Click delete here. Uh, Make sure you choose the reference point, not this guy. How you need to, you can rotate. You cannot select it, okay? And click done. And yes. And then again, create reference point below. Tool, reference point, click here and done. And you go back again to the assembly. Now there are two. We're going to make MPC beam. So the way you create the correct loading is by using MPC beam. It's a multi-point constraint interaction, I think. Yeah, here create constraint. We're going to MPC constraint, continue. Select the control point, that is the reference point. Select the region that will be controlled by this guy, because this is like the loading point, and this loading point will control the block, right? The block will attach to here, right? So this block will attach to here. So we choose that surface here, okay? And there are so many types. I will not explain one by one. I will make another video specifically for MPC, but for introductory purpose, let's just use the beam for this purpose, okay? So the idea is that all these nodes on the surface will be connected to this MPC. And make sure we are using beam. This one is link. I think I made a mistake. Yeah, beam, beam. Okay, beam. And then let's create the second one. MPC constraint. This is one. And then for, yeah, we choose this guy and click. This is also beam and click OK. So now what we need to do, instead of putting boundary condition on the surface, we only put boundary condition on this reference point. That's the difference. So let's go to the load now. Here, let's deactivate them and then create another one, displacement. Click here. Okay, now they were going to be up 100. like before, and we allow for the rotation. Okay, the same thing before we also allow, but since we apply to the surface, this surface remains straight even after the deformation. But here in this case, now we're using MPC and we apply only on this reference point. That's why it allows for rotation of this surface. That's why the deformed shape will be nice, like the real condition. Okay, displacement, this one, everything is zero because this is just like a fixture. Okay, and now let's simulate again. Let's make a with MPC. It should be working fine. Let's make 4. Okay, and then okay, and then job manager. It's still running. Let's check how much it's finished. It's still 28%. I think. Uh, let's stop it or wait. Let's wait. Let me pause the video and wait until it's finished. Right. All right. So now we have started running the second with MPC. Let's now check the one without MPC. This is the result. Wow. See, there's a big deformation. That's why you need to use large nonlinear geometry. And there's delamination here. You want to check the delamination, CSDMG. This is the damage. Yeah, so the surface initially was there and it propagates. It's opened. But the problem here is here. They remain horizontal, which makes it wrong. So for example, if you want to use this model to calibrate the material parameters from the experimental data, using this model will lead you to inaccuracy in the data. And as you can see here, this is also straight. The way the crack propagate is straight. Usually in the real situation, the how to say the middle part will propagate further compared to the edge part. That's called edge effect, as we might see when the other model finish. Yeah, so this is nice. So let me show you first how to get the force time data. Click here, ODB, continue. This is in the y directions. Unique nodal, RF2, node label, node set maybe, internal set. Know which one is this one? There should be a reference point there. Let's check again. Why there is no reference point? Reaction force, RF2. Let's highlight no. That's wrong. Oh yeah. Node set. Okay. So let's check this set one. Save. Okay. Because we apply to all these nodes right in this one. So if you click here, there are a lot of data. Let's sum operate on XY data, continue, sum, click here, and then press shift and click, add the expression, save as, and click OK. Now if you check here, this is XY data 1. Let's plot. So this is the force displacement. So force increase, and then it's like this plateau. Why plateau? There, in reality, it should be like this. And maybe because I put too big damage evolution, so it will not decrease a lot. Or let's compare with the other one without MPC. I think it's already finished quite a lot, like 40%. I think we can already check results. Let's remove this. It will not overlap and will not confuse us. Delete. Yes. Make sure not deleting this one. This is from the previous one, right? You see? Now it deformed nicely, right? Should be reaching 40, 42. You go to here. The damage not yet started, already almost. Let's wait for some times. But here the idea is that it deforms correctly. That's why you need to use MPC beam. Okay, so it can rotate the surface. It's totally different with the previous one. We check the stress here. Looks good. You see here, when you're bending a beam, there is a stress gradient here. And in order to capture that, at least you need to use 4 elements. Yeah, in this case, I'm using 5. And let's go again. Yeah. Start to propagate. And let's check. ODB, continue. Reaction force 2. Where is it? There should be a node label. Okay. So, okay. Save. Okay. Then let's plot this data. As you can see here, they're increasing. Let's wait a little bit. This is still 46. We go to the job. 47. Yeah, but I think you already understand the idea of using MPC. With this video, you already learn how to use, uh, cohesive surface, and then you know how to assign material properties for anisotropic materials, and then you know how to use DCB, how to model DCB correctly like this with a pre-crack, right? So hopefully this video is useful for you. If you like this video and you want to see more videos like this coming in the future, please don't forget to like, share, and subscribe to this channel because it will motivate me to put more videos periodic periodically. Periodic, yes. Okay, goodbye guys, thank you very much. So guys, we try to compare this and this. This is from the previous without MPC, this without with MPC. You plot, the curve is totally different, right? This is with MPC, this is without MPC. As you see, the without MPC is stiffer and the shape is totally different, right? You know why? Because this deformation is totally wrong. You know, when you're loading it, you're not only dissipating energy here, but in terms of bending this beam, which requires a lot of energy. That's why if you go here to the plot, they are way much stiffer or without MPC, right? And with MPC, it's very very how to say very compliance because now it's easier to bend. Okay, let's okay check it. Now they are already have a lot of deformations. 72, still limited delaminations. I'm not sure we did it correctly here because here it's only up to 46. Let's update the plot. That 8, I think, right? Yeah. Okay. And then let's plot them together. See? Yeah. So it's a totally different curve, different stiffness because we performed wrong simulation here because we didn't assign a correct boundary condition. So it's really important, guys, assign correctly the boundary condition when you're doing DCB simulation or any simulations. Bye.